Hello and welcome to another one of D's ADD videos. We're going to continue our Lewis structure discussion by looking at some more of the complex Lewis structures. By complex I mean more than one bond between two elements. Okay? So again, recapping the rules, what you want to do is you want to first count all the valence electrons and then add them up, sum them up. Okay? Draw the skeleton structure with the least electronegative element in the middle. Hydrogen is an exception also. Sometimes if you've got multiple elements, the odd person out would need to be central, even though it might be a little more electronegative. Then you draw in your bonding electrons and you fill in your lone pairs, and you do that to try to satisfy your octet rule. Octet rule states that most of these elements want 8 electrons in their valence shell. You can violate that rule by using the expanded octet rule that occurs in anything with a third period or row or below. Because once you start going there, you started adding your D subshells, and the D subshells allow you to make more bonds. Then you want to calculate the formal charges, and you want the one that has the fewest formal charges with the most number of bonds. Okay? That's a quick recap on the rules. Now let's do some. So I'm going to start off rather simple and then build my way up to it. So beryllium chloride. Let's look at that first. Beryllium's in the second column, so it has 2 valence electrons, plus chlorine that has 7, but there's 2 chlorines, so it's going to be plus 2 times 7. So we get a total of 16 valence electrons. Then we draw a skeleton structure. Chlorine is in 2, so this is probably the way it looks. Halogens usually are on the periphery. They're not central because they have 7. They usually just accept one more electron from one bond. So their inability to form multiple bonds usually puts them in the middle. Alright? So now what do? Well, we start putting in our single bonds, trying to satisfy octets with people by adding lone pairs. And actually what I should do is, at this point, do 16 minus 4 bonding electrons, right? Because there was 2 for each one of these lines. And that gives me 12 lone pair electrons. And if I start adding these lone pair electrons here, 6 for each chlorine, I think that gives me what I need, right? Relatively straightforward. Let's do the formal charges. Make sure the overall formal charge of this thing is neutral indeed. So let's do beryllium first. So the formal charge of beryllium, the valence number is 2, minus the number of bonds. Well, it has 2 bonds, right? One with each chlorine, plus 0 lone pairs. So, or lone pair electrons, not lone pairs. A lot of people make that mistake. So that would be 0. And that's what we wanted, because hopefully the chlorine charge will also be 0. It's in the 7th column. So it's a formal charge of 7 minus 1 bond plus 6 lone pair electrons is also 0. And this applies for both chlorines, so we don't need to do another formal charge for the other chlorine. Alright, so I would say that indeed this is a valid Lewis structure. Okay? There's example 1. Now let's do another one. Running out of space. I am in the virtual world, so I can zoom in and create more space. Look at that. Look at all the space I just created for my little corner. Alright, so we're going to start here. Let's see. Let's do... I gotta change my size of my pencil. This is the simplest alkane. Carbon has, I think I zoomed in a little too much. Let's zoom out a little bit. Still gives me plenty of room. So, methane, we have a total of 4 here, plus 4 times 1 valence charge, gives me a total of 8 valence electrons. If I do a skeleton structure, I'm not sure why my tablet just made a noise at me. I have this skeleton structure here. And at that point, I want to start drawing in my single bonds. Okay. This is an exception to the rule, right? Symmetry and the fact that hydrogen can only form one bond forces carbon, the more electronegative element in the middle. So here I subtract, there's 2, 4, 6, 8 bonding electrons, so we have no valence electrons. That one was too easy, wasn't it? Let's try carbon tetrachloride. Oh, I should do the formal charges, right? 1 valence, 1 bond, no pairs. Fourth column, 4 bonds, no pairs. Excuse me, I have the hiccups apparently. Let's do carbon tetrachloride. That one is going to be 4 plus 4 times 7 is 32 electrons. And again, carbon will be in the middle. This time it is the least electronegative element. We can put single bonds here. Subtract 8 bonding electrons, and then we would have 24 valence electrons. And each of these chlorines are going to have 6, and there's 4 chlorines, so there's my 24. Okay? If you were to do the formal charge on both of these, the formal charge on each and every one of these chlorines, you don't have to do it 4 times. Charge on the carbon is 4 minus 4 bonds plus 0 pairs. So neutral as well. Alright. Let's look at something with multiple bonds. Let's look at carbon dioxide. Alright. So we got 4 plus 2 times 6 is going to be 16 total. And then we have this basic skeleton structure based on symmetry. And now we want to start satisfying octets. So if I put a single bond here, a single bond there, that could be plausible. And then fill in 1 pairs. Let's see how many we have there. 2, 4. You should start seeing that. Let's see how many electrons we have. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So that's not going to work, right? So also you can see that the formal charges of this oxygen, you can try it out on your own. Go ahead. We get -1. This has 1, 2, 3, 4, 5, 6. So we go -2. This one would be -1 as well. So since it's not neutral netwise, then we know it's not correct. So let's try some multiple bonds, and if we do that, we will reduce the number of electrons that need to go as lone pairs. And that looks a little bit better. Let's try it out and see if it works. We have minus 8 bonding electrons. Gives me 8 lone pair electrons, and sure enough, that's what I had. My oxygens. So let's do the formal charges. The formal charge of an oxygen is 6 minus the 2 bonds plus the 4 lone pairs is 0. Formal charge of carbon is 4 minus 4 bonds plus 4 lone pairs. So, yep, that works out. So that's our balance structure right there. Okay, these lone pair electrons might be drawn as straight line. Just straight lines always mean multiple or 2 electrons. Okay, so that's the basic examples of fluid structures. Make sure you check out the examples of the more complex ones, including ions. I hope this has clarified any confusion that you might have and given you a nice foundation to get started to practice as many of these as you can, because practice is what needs to happen. Again, this is key for you to understand the next phase of your chemistry education, which is going to be hybridization. Without a good understanding of those structures, it will be impossible for you to understand what hybridization or how to do the hybridization.